Hi, I'm Craig Putnam from WPI's Robotics Engineering program. In this video, we're going to start talking about sensors and sensing. So let's begin by asking, what is a sensor? A sensor is a way for a robot to interact with its environment, to sense what's going on around it. Sensors can determine, for example, an internal state of the robot, something like how much the shaft of a motor has rotated. And if you were to take time into consideration, you could calculate the speed of the shaft's rotation. You could also determine something like the position of an arm on a robot, or the fingers, the temperature of some internal part of the robot, most anything. You can also detect things that are external to the robot, such as where the robot is on the playing field, or what the angle and distance is to a field object. The bottom line is that if there's something you want to be able to measure, there's a sensor out there that can measure it. There are two broad categories of sensors, digital and analog. The category is determined mainly by the type of signal that's output. For digital sensors, the output is going to be in the form of an output line which can have either the value 0 or 1. This is called a bit or binary digit. You might have multiple digital output lines, multiple bits that taken together can represent some larger numeric value. The simplest of digital sensors is nothing more than, for example, a simple push-button switch. The switch in one position outputs one value, let's say a 0, and in the other position it outputs a 1. Analog sensors generally output a continuous signal, usually a voltage, which is proportional to what's being measured. For example, an analog temperature sensor might output a voltage in the range of 0 to 5 volts, which corresponds to a temperature range of 0 degrees C to 20 degrees C. That voltage range is something that you would determine, the voltage and temperature range is something that you would determine from the spec sheet. So we want to be able to read information from our analog sensor. So you're going to have that sensor output go to that particular analog input pin. And we're going to assume that the voltage range is 0 to 5 volts for our sensor. Now, what we need to do is we need to consider that voltage is varying in time. It can be varying continuously in time. It could represent a light level or a temperature, all sorts of different things. So the first step in being able to deal with the output from that sensor is we need to be able to capture the value of the sensor at a particular point in time. Right? So what we're going to be doing is when we initiate the process of reading that analog input signal, we're going to make a function call or call a method to do that. The analog to digital converter captures the value of the voltage and changes it into a number. The number is typically in the range of 0 to 1023. But where did that number 1023 come from? Well, it's 2 to the 10th minus 1. So where did the power of 10 come from? Well, it's the number of bits in the analog to digital converter. Some microprocessors might have an 8-bit ADC. So the range of numbers that you could get would then be 2 to the 8th minus 1, or 0 to 255. With a 10-bit A to D converter, you can get a range of numbers of 2 to the 10 minus 1, or 0 to 1023. With more numbers in the range, you have the ability to get a better resolution out of your analog to digital converter. Let's look at this visually. Suppose we have a number line that extends from 0 to 5 volts, which represents the signal that we're getting from our sensor. And suppose we also have a number line that extends from 0 to 15 for the values that we could get out of a 4-bit analog to digital converter, 15 being 2 to the 4 minus 1. Here you can see that a large range of voltages has to get mapped into a single number. This is a problem in that we're going to lose some information. It's called quantization error. All right? What we want to do is we want to minimize that quantization error. So we want to be able to have more steps with each step being smaller in size, so that a smaller range of voltages gets mapped into a single number. This improves the accuracy, the fidelity of the analog to digital conversion that we're getting. High-resolution ADCs, that is, ADCs that have a larger range, 2 to the 10 or 2 to the 12 in the range, cost more and are more complicated, but you get better results. So there's an engineering trade-off that you might have to make at some point. A minute ago, I said that the ADC captures the current value of the voltage. But what determines when that happens? Well, your code determines that. Your code will have to call a subroutine or a method that kicks off or starts this analog to digital conversion process. This is called sampling the analog input signal. How often should it be sampled? That's a fair question. Generally speaking, the more often that you can sample the input, the better. However, again, there's a trade-off that's involved here. The more often that you're sampling, the less time your microprocessor has to do other things that it's supposed to be paying attention to. So you've got to balance that. On the other hand, if you don't sample often enough, you might miss something important that happened in your input signal. So it's a trade-off, and you have to pay attention to that, and there's no one particular answer that meets all needs. We've talked about how to go about doing sampling for analog signals. Let's talk briefly about digital signals now. The process of acquiring what the value is on a digital input pin is very simple. You're going to make a function call or method call to do that. The main difference between the digital case and the analog case is how long it takes. For a digital pin, reading that pin is essentially almost instantaneous, whereas for an analog ADC conversion, that takes relatively a long time. So you don't need to worry quite so much about that for digital inputs, but the process is similar. You're going to make a call and get a value back per pin. You may have multiple input pins, and you may need to read multiple of them to collect that information into some other larger integer value. Finally, there's a type of interface called pulse width modulated, or PWM, and this is a signal that's sort of a hybrid. If you were to look at it, it looks kind of like a square wave. The value is either zeros or ones at any point in time, but the way information is conveyed is not through the fact that it's 0 or 1, it's how long the signal is at the 0 value or the 1 value. And that can vary continuously from one range to another. All right? So in that sense, it's more like an analog signal than a digital signal.